Hello all. In today's class, we will see the analysis of LTI system using Laplace transform and a brief introduction to the concept of transfer function. We have already seen how we can analyze the LTI systems using CTFT. In the same way, we can perform the analysis of the LTI system using Laplace transform also. We know that both Laplace transform as well as CTFT applies to the continuous time signals. Let's move on to the basic concept of transfer function. The transfer function of an LTI system is nothing but the Laplace transform of impulse response. We know that the impulse response is denoted by the term h of t. X of t is the input to the LTI system, that is a linear time invariant system, and y of t is the output of the linear time invariant system. Then y of t may be expressed as x of t convolution h of t. This operation is nothing but the convolution operation. Let that be denoted as equation number 1. On taking the Laplace transform on both the sides of this equation 1 and by using the convolution property, we know that convolution in the time domain means it is nothing but the multiplication in the frequency domain, that is in the Laplace domain. So on taking Laplace transform of y of t, we get it as y of s. X of t's Laplace transform is x of s, and h of t's Laplace transform is capital H of s, and convolution in time domain will be equal to multiplication in the frequency domain. Hence, this equation becomes y of s is equal to x of s into h of s. Hence, just rearranging the above equation, the transfer function h of s becomes y of s by x of s. So, this is the final equation of the transfer function h of s, where y of s is the Laplace transform of y of t and x of s is the Laplace transform of x of t. Now, the next topic is how we can perform the analysis of a linear time invariant system using the Laplace transform. We have already seen this analysis using CTFT. This is the Laplace counterpart of analysis of LTI system. We know that a continuous time LTI system is represented in terms of differential equation of the form sigma k is equal to 0 to n ak d raised to k by dt raised to k y of t, where y of t is the output. This is the differential part. This is the coefficient of the output, is equal to sigma k is equal to 0 to m bk d raised to k by dt raised to k x of t, where x of t is the input part and this is the differential part and this is the coefficient part. Such a kind of an equation, it might be represented in terms of Laplace transform by taking Laplace transform on both the sides. That is, you can take the Laplace transform of both LHS as well as RHS, and then you can apply the differentiation property. On applying the differentiation property and taking the Laplace transform, we get d raised to k by dt raised to k. It is equivalent to s raised to k in the Laplace domain. That is, d raised to k by dt raised to k into y of t. It can be written as s raised to k into y of s, and this portion it can be written as d raised to k by dt raised to k x of t can be written as s raised to k into x of s. This ak and this bk, that will remain as such. So on taking the Laplace transform on both the sides and applying the time differentiation property, we get sigma k is equal to 0 to n ak s raised to k y of s is equal to sigma k is equal to 0 to m bk s raised to k into x of s. In the next step, what we are doing is we are taking the term that do not contain any of the k terms. That is, in LHS it is y of s. Y of s is taken outside, and inside the summation we will include only the term that contains this k terms, that is ak into s raised to k. And in RHS we take this x of s term outside, and within the summation we have only the k terms, that is bk into s raised to k. Only these terms are there. And in the next step we will solve for h of s. We have already seen that transfer function h of s is nothing but y of s by x of s, and on rearranging this particular equation we get y of s by x of s as sigma k is equal to 0 to m bk s raised to k by sigma k is equal to 0 to n ak s raised to k. So this is the general format of the analysis of LTI systems using the Laplace. Conversely, this is how we obtain the transfer function from the differential equation. In the same way, if you are performing in the reverse order, we can determine this differential equation if you are given with this transfer function. So in the next two sections, we'll be seeing the problems relating to the differential equation conversion to the transfer function and transfer function conversion to the differential equation. So this is your first problem. Find the transfer function of the LTI system described by the following differential equation. The equation is d square by dt square y of t plus 3d by dt of y of t plus 2y of t is equal to 2 into d by dt of x of t minus 3x of t. So from this particular equation, we know that on applying the Laplace transform and the property of differentiation to both LHS as well as RHS, we get d square by dt square. It can be written as s square. D by dt, it can be written as s. Here there is no derivative term, so there is no s raised to k term. Same way here also, d by dt of x of t means it is s into x of s, its Laplace transform, and this is minus 3 into x of s. That is, if suppose it is d raised to 4 by dt raised to 4, then the Laplace term will be s raised to 4. So taking the Laplace transform and applying the differentiation property, this can be written as all these y of t gets transformed to y of s. So this becomes d square by dt square is s square, d by dt is s, and 2, there is no derivative term, so it is 2 as such, into y of s is equal to x of s into 2s minus 3. And on rearranging, we get h of s is equal to y of s by x of s, which is equal to 2s minus 3 by s square plus 3s plus 2. Hope it's clear. Same way, this is also another problem. That is, here you have d cube by dt cube term. So you will have an s cube minus d square by dt square. It will contribute to minus s square term plus 3. No differential term, so it is just 3 whole into y of s, because in all the case it is y of t, so that will be converted to y of s is equal to 4 into, this is d by dt, so it becomes 4 into s into x of s. On rearranging, you will get h of s is equal to y of s by x of s as 4s by s cube minus s square plus 3. So this is the method by which you find the transfer function from the differential equation. Next section, it is just the inverse of what we have dealt just now. That is, we have to find the differential equation if you are given with the transfer function. That is a question. Find a differential equation description of the systems described by the following transfer function. You are given with the transfer function. So we know that transfer function is nothing but y of s by x of s. And y of s by x of s, it is s square minus 2 by s cube minus 3s plus 1. In order to find the differential equation, you need a y of t term as well as an x of t term. So next step, we will just cross multiply. That is, with y of s, we will get y of s into s cube minus 3s plus 1 is equal to x of s into s square minus 2. Next step, we will take the inverse Laplace transform and we will apply the inverse of the time differentiation. That is, s cube means it is nothing but d cube by dt cube, and y of s is common to this section and x of s is common to this section. So s cube means it is d cube by dt cube into y of t minus, here there is 3s, so it becomes minus 3 into d by dt of y of t plus 1, that is y of s is only there, y of s into this 1, that is y of t. And this section, it is x of s into s square. X of s inverse Laplace transform is x of t, s square's inverse Laplace transform is d square by dt square, minus 2 into x of s. Its inverse Laplace transform is minus 2 into x of t. And this is another problem where you are given like this. That is, transfer function is given as 2 into s plus 1 into s minus 1 by s into s plus 2 into s plus 1. So that becomes 2 into s square minus 1 by s into, this is being expanded. It becomes s square plus 3s plus 2. Again, you are expanding the denominator. So it becomes 2s square minus 2 by s cube plus 3s square plus 2s. That is nothing but your y of s by x of s. Okay, the next step, we will cross multiply. Y of s is multiplied by this denominator section, that is s cube plus 3s square plus 2s, and x of s is multiplied by this numerator section, that is x of s into 2s square minus 2. Again, we can write in the same format. Here it's s square, so it becomes here. S square means d square by dt square. 2 s square means it is 2 into d square by dt square into x of s is x of t minus 2x of s. It becomes minus 2x of t. And here first term is s cube into y of s. That is nothing but dq by dt cube into y of t plus 3 into d square by dt square into y of t plus 2 into d by dt of y of t. So that's all about how you can convert the transfer function into its corresponding differential equation. Hope it's clear to you. That's all for today's class. In the next class, we'll be dealing about causality and stability of the LTI systems and its analysis using Laplace transform. That's all. Thank you.